Hello everyone, how's it going today?
Good.
Having a good time at Hackfort so far?
You bet.
Nice. And can everyone hear me okay, or should I use the mic? Huh? We're good? Perfect. Well, my name is Oliver MacDonald. I am a local engineer here in the Valley. I co-run a company called QTEX AI. We do AI software for hardware engineers, specifically electrical engineers. But outside of that, I am a robotics and systems engineer by trade. Grew up and worked on developing hardware for different companies, be it the electrical side, the mechanical, as well as writing software, which is what you will see a good bit of today. And through that also, if you go to the interactive session, you will see me with the class I teach on autonomous robotics. So afterwards, if you want to see a robot that uses devices like an ESP in it, it is, if you go back through the doors and to the left, you'll see my students out there with a large lunar robot. So with that, the focus of today's workshop is really just to introduce you guys to the ESP32, what we call a microcontroller that you can use for your own home automation. It's just a great little controller in general that you can connect to Wi-Fi, to Bluetooth, and do a bunch of different series of things with. But today we'll focus on how you can use it with something like a temperature and humidity sensor to tell you what the temperature in your house is, or something like this little black switch here, read switch, to tell you if a door is open or closed on your own home network. So raise a hands real quick. Who here knows what IoT is? Good bit of hands. Okay, perfect. So I won't spend too much time on this. As you guys know, this is the Internet of Things, really part of what is considered the fourth industrial revolution, or Industry 4.0, of connecting a lot of things to a network, and has expanded to these little devices as well, as long with your computers, home servers, all of that type of technology. Now, why the ESP32? This is my favorite board. Whenever I'm working on any project, be it a robot, be it something for my home server, my own systems, I by default, even actually for my consulting clients, I by default go to an ESP32. It is a powerful little microcontroller that can run both Wi-Fi or Bluetooth on it while running additional code. So for example, you can use one of these devices to run multiple motors on a small robot and act as a bridge between something like a laptop that runs the heavy calculations on where you want a robot to go, and then pass it off to a device like this to do the lower level calculations of, okay, how much does each wheel need to spin, and telling the devices to do so. It supports, as I said, Wi-Fi and Bluetooth, so it gives you a lot of flexibility within that. It also has the ability to be expanded with something called LoRa, which is a long-range radio antenna for what we call LoRaWAN. So if you have a lot of property out in the mountains or in the desert, you can set up an ESP32 as a bridge throughout your entire property to help get data from different points of your lot. And they're cheap. I bought 3 of these little devices just for today's event, and I want to say it cost me 13 bucks on Amazon. They work, they're plug and play. I spent a bit extra to get USB-C because it is a great connector type and a lot easier to find connectors now than micro B. And besides that, they just work. One of the best things about these controllers is they tend to work very well supported. And as we'll get into here, they work with the Arduino framework, which is a very popular framework for coding on these devices. Now, there's 2 different ways you can configure these. Unfortunately, because I'm running a Windows laptop, ESP Home is being a bit temperamental today. So I will explain what ESP Home is, but then we'll jump into the full code side with what's called Platform I/O. But in general, you've got a few different paths. ESP Home is a no-code, low-code way to set up these little devices if you run Home Assistant, which I believe there was a workshop on earlier today. Home Assistant is a local software you can run on your home, on your own server, that allows you to connect different parts of your home. So be it if I would want to control my lights, set up a device like this to check which doors or windows are open. You can connect, I guess, microwaves, your dishwashers, anything that is now connected with IoT, there's a high chance it works with Home Assistant as well. And they have a dedicated system just for these ESP devices. Platform I/O will be the other thing we go over, and that is the full, hey, we're gonna code this platform, we're gonna have a lot of customization and flexibility on what this device does, how it does it, and what we want the response to be. So, real quick, this ESP32, it runs on 3.3 volts. As Not a big thing, luckily, as if you've got it over USB, USB is a 5-volt system, but these devices, these development boards have a chip that take your 5 volts down to 3 volts. But it's important if you're ever working on some sort of sensor that outputs 5 volts, you cannot run a 5-volt pin into 3 volts. Just thing to note if you ever want to play with these, checking on your voltages for your pins. But besides that, it uses USB for communication. You don't need any other protocols from there, and it does have 2 buttons on the device. We have, as I try and get my orientation right, we have a boot button where if there's ever any issues with the device, and I think I've got it, yeah, on the screen, you can always hit this button and it will just allow you to completely overwrite everything on the chip. And there's an enable button that allows you to shut off the device completely or shut it back on. And lastly, before we jump in, we will be working with 2 sensors. Like I said before, a temperature and humidity sensor, the DHT11, which is an incredibly common sensor used for many home applications and in industry, as well as a reed switch. This is literally just a piece of metal inside of a box that when you snap a magnet to it, it opens a signal. When you remove the magnet, it closes the signal. Simple as that. If you ever buy yourself any sort of window or door detection, that is what's typically inside. So ESP Home, that is the no-code platform. You can do everything over the air. You don't have to connect via USB. You just set up a very simple file and say, here's the pin that this set device is connected to, go. It's very simple. You can run it over Docker as its own enclosed environment. Docker is just a system that allows you to run pre-built code packages as a server. I'll have information on this at the end and can make these slides available for folks that want to run this on their own hardware. This is what that YAML file looks like. This is struggling to format correctly, but it's just saying, hey, the platform, the sensor I'm using is the DTH. We're on pin 4. Here's the name of the temperature sensor, room temperature. Humidity is called room humidity, and we want to update every 60 seconds. That's about it. That gets configured with your Wi-Fi settings, and that gets connected to your Home Assistant or ESP Home with whatever network you have, and that will just update every 60 seconds what your temperature is. All of that you can run through something like the Arduino IDE to program the board, or they have a web platform as well that you can just go in, say, add a new device, this is what I want to add. It's as simple as that. And same for the sensor. For the reed switch, just tell it, I have a basic GPIO, or this is a general purpose input-output. It's on pin 5, it's a door sensor. That's all it needs. Everything goes to your phone, to your home server, wherever you have your data accessible, it all gets stored in this one place. Now that's a super easy, fun, quick way to get these things set up. But being hacked for it, we're going to go through the a bit more complicated, but a bit more fun process, which is working with the code itself. So we'll be doing that through Platform.io. Platform.io is an extension for a tool called VS Code. Who here has worked with code development before, or in VS Code in the past? We got a few hands up, a few who don't. So if you haven't worked in VS Code yet, and you're wanting to get into code development, I highly recommend it. It is a Microsoft software that allows you to manage all your files, packages, and has a lot of great extensions like Platform.io. This is, at this point, an industry standard. I don't know many companies who don't use Platform.io at this point because it has everything you need to just say, I have this device, I want to program it. It builds the tool chains or the processes inside your computer for how to actually put the code onto your device. And then from there, you're just left up to writing the code yourself. We'll talk about this architecture a bit more as we jump into the file itself, but you pretty much initialize the project. You configure any settings you need for the board. You add in libraries, which are pretty much folders of data saying how certain code files are supposed to work. And then you write the code yourself. Now, we will just jump to ESP. And we'll start with the DHT11. This is, as one of my TVs dies on me again. Maybe. There we go. So this is what you'll see when you first set up a project with Platform.io and start working with one of these ESP devices. You've got a few different folders here. I am on the Platform.io INI. This is just my configuration file. I can see I'm working with the ESP32. Espressif is the company that makes ESP. That's the notation for ESP is Espressif. It's just the development board that we're working with, the ESP32 dev, and we're using the Arduino framework, which is a set of code on top of C or C++, one of the core languages, that allows you to communicate with the pins on this board. We have a git ignore. Quick hands, who here has worked with Git before? A few hands. So for those who have not worked with Git, Git or GitHub is Git is a management system for tracking files throughout your computer. GitHub is a cloud-based platform that helps manage files on your computer and store them in a cloud environment. And this is specifically for code. People also do it for actually designing circuit boards and tracking that as well. This git ignore is telling the system pretty much, here are the files I don't want you to track. So things that are very repetitive, redundant, configuration files, the .vs code folder, that's just tracking what's on my computer to run on this device. We don't need that across every platform. We just want to care about the code itself for the device. There's a testing folder, src or source, which is where we will get started writing some code here in a second. There's a library folder, there's that .vs code and .pio. The bulk of this really that you need is just the main.cpp. This is where all of our code will be put into the device. So a quick lesson on code as I clear out some of their initial code here. For these devices, we have two different, really what we'll call functions that the device goes through every time you turn this on. Setup will only ever run once. As it sounds, when you first plug in the device, it will run what's in the setup code. It does that once. That's how you configure the device, tell it to connect to the Wi-Fi, host its own Wi-Fi, whatever you want it to do once. Typically, you put that in setup. Then you have loop. As it sounds, that's where things start to loop. This is really what happens behind your computers on the back end, but very low level compared to something like Windows. This loop is what's run every single time until the device is turned off again. So you'll go through setup, then you'll hit loop, and once you get through all the loop code, you go back to the top, and that's all the device is doing and how it thinks through the process. So if I jump over to one of the systems I have working here and connected right now, this is our little reed switch. I'm going to undo this cable here. This little reed switch, again, is the one that just is configured by the magnet itself. If you watch the notation on the bottom there, if I remove the magnet, if I turn on my serial communication port again, we'll let this reconnect real quickly. So as this connects, the one thing that's happening here is this is called the serial port or serial communication. This is what's actually being sent from this device in my hand to the computer itself. So if I pick up my magnet from the table and I slap it back on, you'll see it's taking a second to update, and now it's closed. And if I pull it off, it's open. And I believe I have a redundancy in the code I wrote 5 minutes ago. So it will keep updating, and it will just keep printing code out to the terminal. The alternative of what I have here as well is, if I can pull my Wi-Fi address here, and I believe I called this state, is an actual printout of, and what we'll get a bit more into is the data itself accessible over Wi-Fi. But alongside that tangent, if I can grab this tab here, this is that loop section that we have in our code. So we start with serial, which we've got serial.begin, which just says, hey, I want to be able to communicate with you over USB. Pin mode is just telling, for each pin on this device, I'll pull the phone off this guy, each one of these pins, anything that is considered a GPIO, or, and I'll pass this around here in a bit, has a little D notation and a number on it. We need to tell the device what type of pin, what's that pin's number, and how do we want that pin to work. So in this case, I have read pin, which is a notation I've stored at the top, just as 15 to make it easier for me to read. But we have read pin, and then we have input and underscore pull up. Input is just telling the system, hey, this pin I am connected to, the pin I have this little switch plugged into, is taking power in, is receiving data, power, some way or another. I want to read the electrical signal on this pin. Pull up on the end of that means at your default state, connect me to power. And there's a bit more electrical stuff going on in the back end, but the reason we pull up is because it allows us to stabilize our signal. This little switch here is connected between the actual pin that we're talking to and what is called a ground pin. The best way to explain this is think about how water flows from, if you have a reservoir at the top of the mountain and one at the bottom, water will always flow down. What's happening is when this switch is closed, think of it like I just opened some sort of valve. Water is flowing from the top to the very bottom. Now, if I were to open this switch again and remove the magnet, well, now we have just this reservoir of water sitting at the top. This is where things get a bit more complicated. Things can shift up and down. The device might think the water is flowing. It might think it's not. So by default, we just say, hey, we have our main pool of water. Let's just have another pool of water and connect them. On the same level, they assume they're not changing, and it makes it easy for us to say, hey, the data going out, we know is actually going out. That's where electronics get a bit more complicated, and as an electrical engineer, I can't really explain more than that, because even in industry, we call it black magic. And when something catches on fire, we say the magic smoke has left, and that's why it doesn't work anymore. So that's where things get a bit more finicky. But in general, we say pull up just to make sure the data comes out the right way. So back to our setup. There's a bunch of stuff here that's just me configuring connecting to Wi-Fi, configuring saying, hey, whenever I go to your IP/state, I want you to respond with this little function up here with this information. And then at the very end, I just want you to tell me over USB this is started. Then we get back to that loop. We're at the very beginning. Every time we run this, we first want to check, hey, is someone asking me for data? Is someone on their computer putting in my IP/state and wanting to get something from me? Now, because of how these devices work, because we manage every single process one by one, if we don't include state here, or if we don't include that call, that check for the API, our system will never check. It's not like Windows where it has a built-in system to always make sure what you're running is always running and have what we call a timer or a scheduler running behind the scenes. We manage all of that ourselves. So that's what we first do every time is say, hey, what's happening? Is someone trying to call us and ask if we have the data they want? Then from there, we can go through and start working on, well, what's the state of what's happening, what's going on through the system. We can go through, we can do what's called a digital read, which is just saying, tell me if this is a 1 or a 0 from this pin, and then just store that as a value called state. And then from there, the rest of this is just what we see on the bottom here of actually printing out what the state of this system is. If I wanted to, I could just say, hey, this is unimportant to me, and remove it. And then I'd have to rebuild and send all of this back to the device. But in general, that's all that's happening here. That is the entire thing you would need to code to set up this little device with this magnet on your door and a switch next to your door and say, hey, is my door open or closed? Now, this you can all write by hand from scratch. And I highly recommend you do, because it's really good to get an understanding of how this code works, why it works, the structure of it. But because this is a short workshop and we don't have too much time, I'm going to guess a good few of you are familiar with Claude or Claude Code. So luckily, a lot of these systems are very well documented on GitHub and are well known, which means Claude can do a very good job at writing this code. For those who are not in the coding field, Claude is a great tool for writing code that has been done before, that is known, that is in the code base. If it's something that isn't in the code base, typically you'd want to architect the system yourself. And even regardless of if it's in code base or not, you want to understand what's your system, how is it defined, how it functions, and what those ideal goals or outputs are. And then we can put that into Claude. So in this case, I can say I have a DHT11 sensor on a ESP32 connected to pin 15. Write a simple code file that exposes the data to serial. and slash data. I'm going to do slash like that. And that's the bulk of it as well. So if you're wanting to not mess around as much with code, but still play around with getting these devices up in your house, you can just pass this off to Claude and get it to write code for you. You'll notice here, it's just going to start running things for me. It's installing my libraries, which I'll explain here in a moment why we need those. But it understands what I'm working in, that I'm working in Platform I/O, what those calls are, and how to work within my file system. I have not given Claude permission to do anything outside of this folder. But within this project itself, I sort of just have given it free rein to say, hey, go in, write code, adjust, do what you need to do. And with that, we have a code file that I would give probably a 90% chance of working. This is the joys of hardware is whenever you're writing code and you're testing code on the computer, it can do very well because its feedback comes from the computer itself. The second you introduce something off the computer or a little device, a microcontroller, it can sometimes read data over USB and get that feedback and try and fix that issue for you. But you have to do some work in between more often than not and help say, here's what I'm getting from the device. Now how might we approach this? So what I'm going to do is first off, quickly put in the Wi-Fi that I'm going to connect this to. And I need to make sure I'm spelling this correctly because this is character sensitive. Or it is sensitive to the capitalization for 2025, 2026. I'm split between two places. And I am just going to say, ignore this password real quick while I type this in. But it's plain text, so it's just going to be right there. In general, for most cases than not, because I know we have cybersecurity people here in the room, this is not necessarily unsafe once it's compiled to the device itself. Once it's on here, you cannot pull the code off of this device. Technically, you can do what's called a hex dump, which will give you every single 1 and 0 inside of the device itself, because that's what this all turns into. This gets turned into a set of 1s and 0s, and that's what the device works off of. I have yet to find a single engineer or any project that's been able to reverse engineer that data, because that would be a monstrous task. This being plain text in my computer is not the safest. I would want to keep this file protected, store this data, not send this up to GitHub so it's in a public folder where people can access this data. But in general, once something goes from this system onto your device, there are some concerns about encryption and data security if you're working with something storing files. But in our case, we're not dealing with that today, so it's not too important. And then lastly, I will include this little guy highlighted at the top. This is what we call a library. We also are using them for Wi-Fi and web server. A library is a pre-built set of code that someone else has built and we are using, in this case, to communicate with this device. I don't want to have to go through and reverse engineer or go through the documentation to say exactly how this device works, how to communicate with it, how to read the one sensor pin, which is, I believe our center, the orange little data line there, every single time I want to work with this. So luckily for me, I didn't design that temperature sensor. Someone else did, and they made a library called DHT, which I can just bring into my system. I can call it as an actual part of the code, a function, a file, and I can say, hey, create a DHT object. It's connected to this pin, and there's a few different versions of these sensors, so I'm going to give it the version of the sensor itself, this being that DHT11. Another common one is the 22. So I can just pass that information, and now it will just work for me. I can tell it to start reading data, and later on, I can tell it to actually read that data from the device itself. So I will disconnect our read switch here. I will first click this little check mark at the very bottom there, the build button. This is just going to tell me, is the code going to work? This will not run it on the device. This will not program the device. This is just going to take all the code, compile it, which is what we mean by taking that code and turning it into machine code, those 1s and 0s, the file that these devices can read. And then after an amount of time, it depends on your system as well as how much code it has to process, it will give me that lovely success thing, which is really the only thing I care about. When you're working in industry or working on bigger projects, those two highlighted bars can be important. RAM being, as we've all seen with the AI boom, as incredibly expensive, is the memory that a system can access quickly or frequently, and is where temporary knowledge tends to be stored. Flash is the physical storage space. Think of it like your hard drive in your computer where you store your files itself. So this code file is taking about 73% of the space on this device. So I can't put too much more on here. But in terms of RAM, I'm only working with 14%, which means this computer still has the ability to process a lot of information. So now it's built, well, it says it should build fine. So what we can do is just plug in the device. The joys of having software that tends to just work is we can just hit upload. And theoretically, it will go through. If I click on auto here, it will look at the different communication ports on your computer. It tends to guess pretty well which one is the one we want to use. In this case, I know it's COM4, but the computer will guess that. And it's going to throw a fit because I opened up that panel as it was trying to upload. So I'll run this again, and we will just let it connect and run its system here.
Regarding that disk space at 75%,
yes.
Your code file is pretty short. Is that because you're using a bunch of libraries that it's filling up?
Exactly. Yep.
Often run into problems of running out of space.
I don't tend to run into files running out of space. That is pretty rare. A lot of it comes from the libraries that you build into your system. There, in the past, when I'm working with a really tight system, I'll run out of space. But that's typically only in industry where I don't have the freedom or the budget to just say I want one of these devices with a lot of space on it. It's also, I went for the cheapest ESP I could find, so they have a bit less storage on these devices than on some of the other ESP devices you can buy on Amazon. It all really depends on what you need. But that 72% or 75% of storage, I could probably write another 5-6 files worth of code and put that onto the software and still be fine. A lot of it is just those libraries that fill up that space.
So if you were wanting to, let's say, expand this to 10 files or something, you would maybe cut out the web server files and some of the other libraries?
It depends, yeah, on what else I wanted to do. Web server we need if we want to expose this data as an API on our network, and Wi-Fi we need to be able to connect to the network. And those, honestly, are going to be our biggest packages on here versus something like the DTH package for the temperature sensor. And a question over here?
I was just wondering if you wanted to do any sort of like, kind of to the point of storage or files being written, if you're doing event logging or any sort of logging for like what's happening with the device, if you, or really how you would tackle like moving that or storing that separately to make sure it's not overloading what the device needs to do.
Yep. Yeah, so real quick, I will show what I do for that, and then I'll explain why this is giving me little diamonds with question marks here. I'm going to go the simple route of Amazon, and I'm going to type in SD card reader. Typically, if you go to Amazon and you type Arduino, it's somewhere in your search. You will find something compatible for these devices. And I introduced to you the SD card interface. This provides the ability to just connect an SD card to one of these devices. There are packages or libraries for this as well. And this is how you would store data physically. There are other, if you're designing an actual board yourself, there's what we call a flash module. That would be the physical data we would store on here. We'd program to the board. We can work with flash as well as EEPROM. A bit more complicated. This is just, hey, we have a communication protocol called SPI, and we can plug an SD card into it. And you're good to go from there. That's as simple as it gets. Again, if you need something to plug in, type it into Amazon and type Arduino. More often than not, especially for home practices, for home IoT, it's going to have something for you there. You can do everything from temperature and humidity sensor like we have here. I know there's dissolved oxygen sensors. You can get sensors to put in your garden to say, what's the pH? What's the conductivity? What's the potassium in the soil? All of those sensors just exist, luckily, because they've been designed for us already. So I'll jump back to here, and there's one small error that Claude made, mainly because I didn't give it the right information. So if I like to not highlight that, right now, this 9600 number that is highlighted, that is what we call our baud rate, or it's our communication speed that the device here or that really the computer here is trying to read from the device at. But when Claude threw this in, it went with the common number of 115 to 100, which is what this device is outputting data at, which is why we get this really random ASCII output that looks like nothing, because we have one device communicating pretty much in Spanish and the other in English, so they don't understand each other. Now, if I were to go through and adjust that rate to match what our computer is expecting, I will build that again. And now, after this builds, we should be able to get information from our system. And this is one of the longer processes that you have here. There's no way to speed this up. You just have to wait for the code to compile and build. And I'm going to close this down, open this back up. Another key thing there of why it errored, we had that serial port open. We had that ability to talk over USB. You can't talk to something when you're trying to overwrite its entire memory. That doesn't work very well. Unlike brain surgery, we can't have someone talking to us while we're messing around with neurons. We need the device to not be functioning so that it connects. Or it could just entirely die on me. So we are going to hit the boot button and run it again. And this is one of the problems you'll run into working with something that communicates over USB, is USB takes up that one line of communication. So now that I rebooted the system and said, hey, stop talking to me, I can now overwrite everything on the chip and be able to write data back to it. Perfect. And then I can click the little plug to open back up Serial. And it's going to try and connect to Wi-Fi again, and then should be able to give us data from there. And there we go. It's now working. Our temperature is 23 C. Our humidity is 19%. And if I pull my little Wi-Fi address here and go to that address /data, I can now pull that information as just data provided to me to connect this to any of my other systems. If you are, for some reason, on a network where this is exposed to other people, if for some reason, let's just use a coffee shop analogy, you connect this device in the coffee shop to the coffee shop network, anyone can access this information. There is no password protection. There is no encryption. This is just publicly available. On your own home, it's not as important. Unless for some reason you have a kid who's going to go in and screw with the stuff you set up, anyone can access this and that should be fine. Otherwise, you might want to go in and set some sort of encryption or some basic password so that this data is protected. And there's frameworks for that with API calls that can be done. But in general, now I can refresh this page as much as I want. The data will update every time. And that's really the big thing I wanted to go over with this, and leave some time for questions here. But just a brief introduction to the things you can do with these little devices, because they are fun little hardware pieces that aren't too difficult to get together and get working. I mean, I think in total for all the sensors I've got here, I maybe spent $30. All the softwares I'm using here are entirely free, and they run on Windows, on Linux, on Mac. So any computer you have, you can write this code yourself and work with it yourself. And yeah, get yourself something to ultimately just plug into your network and run from there. So that puts me just about where I want to be, to leave about 10 minutes for questions. So what questions do folks have? And I can also, if there's more questions about like what other capabilities can we do with this, I'm happy to bring stuff up for that as well.
Can you speak to the debug loop like you're talking about?
Yes.
Specifically hardware debugging for someone who doesn't have a double E degree or
Mm-hmm.
whatever. Like you knew to look for the USB connection, you knew to look for the
Yep.
How would you go about teaching someone that?
Yeah, so the serial connections and the USB, those are some of the things that are just, that's more of like me telling you, hey, as you're playing around with these things, check those things always, because they're the most common hiccups I see, especially when teaching students how to work with this. Outside of that, like we could even look at, for some reason, it's outputting a bunch of gibberish. And for this, it would just be a matter of playing around to understand what it might be. If you're brand new to coding that, You can use Claude, you can use ChatGPT, you can use Gemini. I typically just take an error and throw it in and don't really give it any other context. If it has questions for me, it'll ask them. It's a mathematical model trying to predict what I want, so I'll let it predict as best as possible and give me something that is probably not the best answer, because that's the thing I just turned around, but it will try and fix things occasionally for you. Now, outside of that, a lot of it's going to come down to Googling. Even for me, even in industry, every time I get thrown a new project, there's oftentimes where a client asks me, hey, we need a device that stores data in this specific manner. And I look at them like, cool, I know that can be done. Don't know exactly how it can be done, but I can go figure it out. And then from there, you can go say, even for here, I could go to Google and say, I am getting this. I can get this before it updates from my ESP32. And a lot of it is really just relying on other people who have gone through this process as well. ESPs are very common, which is why I also love to start people on them, because there's massive communities out there based around the ESP32. So this one uses the Arduino system for configuring your code, compiling your code, but does a good job of explaining like, hey, here's that COM port, here's the right USB to check, and drivers, all of that tends to just exist out there on the internet. But from there, it's really just playing around with it and getting a feel for it. A lot of my knowledge working with these devices didn't come from an engineering degree, and honestly didn't come much from being just a person in the industry. It came from working on projects themselves, first at home, and then whenever clients would be like, hey, do this, and I'd be like, cool, I have no clue what you just told me, but I guess I'm gonna go Google it because I didn't get to choose if I was gonna take on this project or not. So a lot of it comes down to just being able to search well and understand we have the internet as a search tool, not just ChatGPT, Claude, those tools, but good old-fashioned search, the same way we did it before Claude came out, or ChatGPT was released. I guess it's been 6 years ago, roughly now. So yeah, 3? Has it only been 3? I feel like my students have gone downhill faster than 3 years, but okay. What other questions do we have?
Is there a possibility of like daisy chaining ESP32s?
Yes. So there's a few protocols for this. The main one is called ESP Now. I'm just going to pull up Espressif's website on it. ESP Now is the protocol Espressif themselves, the creator of this chip, which is the actual silver part of this device, built for these devices. What ESP Now allows is for these chips to work as their own routers, which you can no longer buy from outside of the country, so you might want to buy something like this if you need your own small location router, but it allows it to act as its own router, meaning you can build a Wi-Fi network off of this device. If I don't want to connect this to my own internet, I can have it host its own internet, like a printer or like a washer or dryer, or whatever new technology we have that has its own Wi-Fi. I can configure it to connect to Wi-Fi. You can also configure them to mesh and to connect as a group or ping and pass over and over again. It gets a bit iffy depending on what you're trying to do. You can only ever be connected to or host one Wi-Fi network off of the device at a time. And that's because this black bar at the top of the antenna, we only have one of those. You need one antenna per connection or for every output or router you want to set up. So another thing people will do is, we've got multiple of these, we're just going to pair them together. We will set them up with communication across them. One of these is my receiver, one of these is my transmitter, and that's how they'll get data out that way as well.
What are some other sensor examples you brought up?
Ooh, there are a lot. You can do GPS. The GPS sensors exist. One of the common ones that came out was millimeter radar. Millimeter radar is just a different form of radar like you see in the movies, on ships, but it's a very small wavelength to the point where you can actually track someone's heart rate. People use it a lot for tracking people throughout their houses to know when to turn lights on and off. There's a system called WLED. This is built to run on ESPs and different devices. WLED controls those different, like, think of like the Govee LED strips that you might have in your house, or different LED strips that you can put around the room. There's an entire YouTube channel actually dedicated to ripping apart products on Amazon and putting an ESP32 in them to make them controllable by your home network. So that can all be connected. Again, we've got plant sensors, dissolved oxygen. You can build a lot yourself as well. Set up a little motor to hit a button somewhere in your house, or to see if a button's been moved. We use infrared to check if you've crossed, sort of like the spy movies, the laser beam. You can use infrared to check if something has passed. Your backup sensors on your car use what's called an ultrasonic sensor, which, similar to radar, just sends out a sound pulse. You can use that to see how far something is from you or from the device itself. There's a lot you can run off of these devices. The sky really is the limit. I could run a full robot off this that could see the world around it, get information, track where things are, all with a single device. So it's pretty open. Yes?
Do you have these installed at your house? Like which ones do you use personally?
Ooh, I don't have too many of these installed in my house right now because I am rebuilding my entire network for the 7th time. Because I get too picky about how I want my configuration to be and then have to rebuild it. Right now, what I'm working on is getting the plant system up first, which is why I know the most about that one. If I go back to Amazon here, I will go Arduino, plant conductivity. See if it gives me the 3-prong. It might be under another name. So anyways, there's a bunch of different types of things you can do with these. These are, if Amazon wants to let me increase the image, these are little humidity sensors for soil. So you can set up one of these devices with a pump, have it read what the humidity of your soil is, and then say, hey, if the humidity drops too much, my plant needs water or it's gonna die, like the last 50 of them. Give it water again until humidity increases. So that's a very simple one I'm working on right now. Outside of that, working with WLED to just connect a bunch of lights together and be able to run all of that off of my phone. There was a workshop earlier today, and I think there might be one more. If not, there's tutorials online of setting up your own server, setting up Home Assistant or other platforms to just connect these devices to. Because at the end of the day, it's great to have them in your house and have them accessible. But for the things I do, I also love to have these monitored from outside of my house, be that with a VPN, be that the risky play of making it exposed to the internet where anyone can potentially find it. There's a lot of different things you can do in that regard. Mm-hmm. Yes?
Kind of on the plant system you're making, is there like an API that you're using to get like plant information, or are you like having to figure out, okay, for a spider plant we want this?
That one I'm sort of just guessing.
Yeah, okay.
Yeah, it's there is no API for that. There are multiple databases that talk about what's your potassium be in the soil. Actually, I might be able to find a potassium sensor here. Potassium soil.
Are you doing like a full featured one for yourself then for the plants, like with all that information?
Yeah, that's the goal, is to be a full featured one. Because ideally, I would like to do an aquaponics system where I can measure a lot of the information I would like. I was hoping I'd find one that would
And my
talk.
next question would be, are you
Yes.
documenting that at all, that we can check? You know,
Theoretically, there's documentation. It's across a lot of files right now. But yeah, a lot of these projects, my goal is to release them as open source projects. There's also countless people who have done this as well that have made their projects open source. And there's a very specific sensor I am looking for right now. Soil pH. Yeah, the joys of also finding things on Amazon is that it changes very often, especially as there's a few. So there is one device I'm looking for that has 3 prongs. It does the pH of your soil. It will do the conductivity, which is important in all regions, but depends on plants. And that's literal, like how much electricity can transfer through the soil, because that has an effect on the actual plant roots itself. It looks at potassium in the soil. There's one other value I'm missing right now, but it can pull all that information together for you. But ultimately, the goal is just to say, hey, this is all here. You can go look up the information online, or you can go to like your Zamzos and go bug one of the employees and be like, hey, how do I grow this? And then take that information and put it into your computer so it can automate it for you. But a lot of this just exists as just technologies you can download, you can buy, run on your computer. There's a lot we can do right now with technology. And even if you're newer to electronics, the nice thing is, and this is what I tell a lot of my freshmen as well, who jump into electrical, is at the end of the day, it's A to A, B to B. This is power in. I bet you it's probably 5-volt power. If I run down, everything is documented. This is a very poorly documented system, but they all have their information somewhere. But at the end of the day, if something says, here we go, working voltage. If something says it takes 3.3 to 5 volts, you give it 3.3 to 5 volts and it works. That's this welcome to industry, where all the math we learned in college doesn't really mean much, because I get told this needs 5 volts, I give it 5 volts. There you go. Same thing for data, for connection. I see this says ground, I'm connecting it to ground. I see this says data, I connect it to a data pin. That's how a lot of these systems work. That's why I always enjoy being at events like this, helping with my students, because at the end of the day, most people have the ability, really everyone has the ability to work on electronics. They're not these complicated systems where you have to go back, do math, look at, oh, how's my current changing versus my voltage, and how do I calculate this perfect value? It's, ooh, I really want to measure the temperature of my soil or my bathroom water or something in my house. I'm going to go throw this on an ESP and call it a day, because that's things we can do.
What kind of projects are your students doing?
So,
Or want to do, let's say.
want to do, they have a lot. Everything from radio projects to just small little robot control. For the class I teach, they work on a lunar robot. So they build a pretty large robot that drives around on the fake moon in a simulated lunar dirt, so the closest thing we have on Earth to what's actually on the moon. And they pick up that dirt from one area, dump it off in another. The entire goal is for them to go to a NASA competition in Florida and really compete against, last year it was 30 different universities, where the entire point NASA wants is to help build infrastructure on the moon. So that's the big thing they do. We do the mechanical teaching, the electrical, the software. We have some IT, which I've stolen your colleagues' contact for to get your students in there as well. But we also do technical marketing and project management, because a lot of engineering isn't just the engineers' work themselves. A lot of it comes from just who has the idea for a different approach that might be something we didn't think about previously. And by pulling a lot of those communities together, we're able to get a lot of work done there. Yeah. Sweet. I think we are just at time. If you have any questions, please feel free to let me know. And I will be in the room with the robot here till 5. So feel free to snag me after if you need anything.